Okay, now the fourth step, that is first we discuss about the problem, then the geometry, then the meshing. Now setup. So double click here, and this is 3D case actually. So I will use double precision solver for more accuracy, but not required actually. So click on the start. Okay, so we have the geometry here, and okay, this is a mesh actually. First thing that I don't like is these like a grid lines here, so and the shadow, so you can turn them off. Okay, then you can this is going to be the pressure based order because the Mach number is less than 1. Okay, less than 0.3. Okay, so velocity right now we have the like a 43.8, and speed of sound at the sea level is 340, so it's less than 0.3, and I don't expect this is going to be anyway this is going to be compressible fluid. Okay, so that's why even you can try to reduce this value to the lower side also, but 43 is okay. Okay, so first thing is that we can display the mesh, and you can hide the few things here and there. Okay, symmetry 1 is on the other side. Okay, you can change the colors also, and you can make the color by the surface ID. So these will be random colors, and every surface will have the different colors. Okay, the only thing that I'm not satisfied is the mesh transition here, but that's okay actually. Maybe if the flow has a laminar turbulent transition and somewhere this location, this may make the issues, but okay, this is okay right now. Okay, so in the models I will keep the default SST model, but for external aerodynamics also I highly recommend that you should use the Sparrett-Elmhorst model. That's a very good model. And also K epsilon with a reliable option and enhanced fault treatment. This is also a very good model. So my best, my choice is K epsilon reliable enhanced fault treatment in the Fluent. Second choice would be the Sparrett-Elmhorst, and third choice will be the K omega. And you can also change the default settings. For example, in the preferences, you can change many things here. And one of them is the which default setting should be in the on your screen. And one more thing is with the K omega SST model, there's a curvature correction that is actually a very good option for when you are solving the flow with a high separation, not wall bounded flow like the aerofoils, but the U band or 90 degrees band. In that case, the curvature correction option is very good. Okay, but that is a separate discussion here. So now you can keep the Sparrett-Elmhorst model or K epsilon or the K omega SST is your choice, and click on the OK. Okay, so I was talking about that. You can select the default model, so that will be effective from the next simulation. Okay, so that can also work very well. And in the graphics, if you want, you can remove the these effects, showing the reflections, that you can turn off. You can turn off the dynamic shadows. You can turn off the ground plane grid. So these things actually you can turn off directly in the Fluent from here. Okay, for the preferences. Okay, so now we have the these all settings are done here. We have selected the viscous Sparrett-Elmhorst model, and in the material properties I will keep the default settings because already when I calculated the settings, I have made the calculations based on these default settings. So at the standard temperature pressure conditions, so it's exactly they are same, 1.225 and 1.7984. Units are Pascal second or kilogram per meter second. They are exactly the same values. One is the a simplified units, and Pascal second is a secondary unit. So, but eventually they will be equivalent. Okay, so just keep as it is. And in the boundary conditions, make sure that you have the proper boundary condition types first, and then the boundary condition values. So two symmetry conditions are there already on the two sides. Aerofoil is a wall condition, nozzle ball condition, inlet. And before that, when we, okay, one more thing that I want to differentiate here, when you are solving the compressible flow, in that case, we put all the pressure into the inlet and outlets. So in the physics, we change the operating pressure to 0. Okay, that's like a atmospheric pressure, and we add the gauge pressure to the boundary conditions, and summing both values will give you the absolute value. But in case of when the flow is incompressible, in that case we just keep the operating pressure, which is actually same on the everywhere. Okay, so as it is, and we put the only gauge pressure on the inlet and the outlet. Okay, and for case of when the flow is incompressible, usually speaking, we provide the velocity inlet. So only thing is that the static pressure is given there, that is again 0 equal to 0, and same is the case with the outlet. Okay, so now for the inlet, this is a velocity inlet, we are going to provide the velocity value, and that is equal to 43.822. Okay, few more things that we can discuss here, that is the value of the turbulent quantities. Okay, so here you have to select the magnitude direction, because I want to put the flow along the x direction. Okay, so right now this is 0 angle of attack case, and velocity value is going to be equal to the 43.822, and gauge pressure is 0 because the operating pressure is 101325. So absolute pressure will be 0 plus 101325 equal to 101325 absolute pressure. And here you can choose the intensity and length scale. Usually speaking, for the wind tunnels, the turbulent intensity is around 1 or less than 1, depending on the case to case. Old wind tunnels will have the large values, the new ones have the low values. And the length scale is typically taken the scale of the geometry, that is right on 1 meter. But it is like from the papers it is said that the AD size that is going to be generated by this aerofoil will be the 30% of the chord length, that is the 0.3. Even maybe less, but 0.3 is a safe guess. Okay, click and apply here and close. In the outlet, you don't need to change anything, it's a 0 gauge pressure, that's all, just check it and close it. Okay, and also in the report definitions, in the methods, I will keep the default settings, coupled solver, momentum second order, and everything is exactly same. In the controls, I will not change anything at all. In the monitors, I want to give the monitors that it should not like stop before I want to stop it. So either you give the very, very low values, or go to advanced options and turn off the convergence criteria. Okay, now solution will not stop based on the convergence criteria, but solution will stop when you want to stop it by clicking on the stop button on the bottom, or when the number of iterations are completed. Okay, then also I want to initialize, and before that I want to put the report definitions for the lift and drag coefficient. So new force report drag, and it's a drag coefficient aerofoil. You can put the name as the drag coefficient. Okay, so for drag coefficient, this is along the same as the direction of the air, that is the 0 degree. So with x component will be 1 and y component will be the 0. Print to console and click on OK. For the lift coefficient, it will be the opposite value, because the lift coefficient will be, one component will be the negative x-axis and one component will be the positive y-axis, but the values will be flipped. So now angle will be with respect to y-axis. So x values will go to the y component of the lift coefficient, and the y component will go to x values, but the x value will be negative. Okay, so the force support and the lift. So here this will be the 0 and the 1. Okay, their values are flipped here, but x will be 0 minus, not minus 0, because minus 0 plus 0 is exactly same. And this is the lift coefficient, and I put the name as the lift coefficient. Okay, print to console as well. This will actually give us the idea that the how solution is converging. It is converged or not, just looking at the line. If line becomes a straight line, then the solution is converged. Otherwise, you have to run the case for the more iterations. So click on OK. Now run the calculation. Time scale factor, right now I will keep the default value, and number of iterations I will go for the 500. But for these cases, with a coupled solver, this should be solved within like a 500 iterations. They are more than enough. So hit on the calculate, and okay, it is saying that you should initialize solution. You can initialize directly from here, or the run calculation will also do it by itself. So both are okay. Okay, so this is done, and now you can run the calculation. Okay, so solution has run for the some iterations, 78, 79. I'm stopping here, okay? You have to run for at least 400 to 500 or 300, 200, whatever it is. But looking at the lift and drag coefficient plot, I think this is done. Okay, but you should run it for the more iterations, okay? Now go to results, and from here forces, click on the print. Okay, but before that you have to put the reference values, and this time the chord length is 0.3. Chord length is the 1 meter, and so let me draw it here. The chord length is equal to 1 meter, but the aerofoil third dimension is equal to the 0.3 meter. So its area that is going to be facing the wind is equal to the 1 meter by the 0.3 meter. So this is equal to the 1 into 0.3 is equal to 0.3 meter square. So you should provide this value here, and velocity should be here. So I will do it. I will get the velocity directly from from inlet. So get the data compute from inlet, and the area you have to put it yourself. Okay. So 0.3 meter square, and then now click on the print. Okay. So you can see the drag coefficient is 0.0122, and what is the value of the drag coefficient zero angle of attack for the NACA 2412 aerofoil? This is equal to the .007 .008 actually. Okay, it's equal to 0.008. So 0.008 is the value, and what we are getting is a 0.012. So once the solution is converged fully, you will get the values close to this value. Okay. Okay, now if you want to run the case for the second angle of attack, so right click here and click on the duplicate. Okay, and please note that you have to run this case for at least 500 iterations to be on the safe side. Okay. Okay, you can rename this file. So angle of attack 10 degrees, and which model we are running here? We are running the SA model. Okay, so that you can also put in the name. Okay, and you can copy this whole name, and you can rename this one and paste it. So this is going to be the 0. Okay. Okay, so now double click on the solution and open the Fluent session here. Okay, so close this first session. Okay, here we are going to be providing the boundary conditions again. Only difference would be the angle of attack. Okay, so on the inlet. Okay, so I have already given the those values in the slide. So for 10 angle of attack, you have to provide these two values. Okay, so in the x direction, this value will be there, and in the y direction, the second value, that is the sine of the 10 degrees. Apply and close. Okay. Okay, also if you want to change, you can change the angles also in the lift coefficient and the drag coefficient, but not required actually. We will calculate lift and drag coefficient directly from the results and forces. Okay, so just run the case. Okay, so I have stopped the solution. Now you can find out the value of the drag and lift coefficient. So my idea or the way I do it very simple. So I will copy the X and Y components. So it depends on the which component you have to copy. So right now the angle of attack is in the X and Y component. So I will directly put them here. X into X and Y into the Y. Okay, and select the arrow file and click on print. So, and also you need to put the proper reference values. Make the area 0.3 meters square. So value is 0.02577, and the case I solved previously, it had the values of the drag coefficient should be equal to the, at 10 degrees it should be the point 0.173. So it will converge actually to the lower values. Okay, it will change. Okay, now in order to find out the lift coefficient, what you have to do is that you have to put the X value into the Y value, and the Y value will be X value, but this will be in the second quadrant, so this will be the minus value of the same number. Okay, minus value from the Y direction values. Okay, click on print, and you get the lift coefficient, that is the 1.23. Actual value or the reference value is equal to the okay, let me open it. Okay, that value is equal to the 0.0125. So definitely this will converge. This will converge. So, and the lift coefficient at 10 degrees angle of attack is 1.25. Okay, so it is very close now, right now. Okay, so both values of the lift and the drag coefficient is 0.0257 right now, but its actual value is equal to the 0.0125. Okay, so here is a slightly higher value. Okay, so it will converge. So you have to run the case for at least 400 to 500 iterations. That's all. Okay, so here you can see the results and my comments here. And also the next thing is that I plotted the CP plot, but actually I have told you that the CP plot that we should be showing, it should be in this way. So how this can be done? It's a very easy actually. If you go to XY plot and from here choose arrow file along the X direction, and it's going to pressure coefficient, and click on the like a save plot. So on the this is the case for the NACA 001. This is symmetric arrow file. That's why at zero angle of attack, both top and bottom side, they don't have the they have similar results. But for the like a cambered arrow file, you will see that the both values will be different. Okay, so that is plotted here. This one. Okay, so now simply you have to write it to the your computer. Okay, like this one. This is the CP 10 degrees. Okay, so open the Excel sheet. And from data, from text file, then go to the new folder and look for that file, all files, and it is going to be where? Okay, here it should be here. This is the CP angle of attack 10 degrees. This is too many values actually. So it is depending on the number of actually the cells. Okay. Okay, around values are around 4,000. Actually, what we should be doing it not like in this way because it's 3D arrow file. So I suggest that display. So you should get the intersection of the arrow file and the symmetry 1 or symmetry 2. So from here results create, and this is isosurface, and okay, it should be like create the iso clip. Okay, just a minute. Okay, you can see here that the okay, you have to click on the z coordinate. Its value is from 0 to 0.3. So let's put the value, middle value 0.15 and click on create. Okay, now the xy plot, and okay, the same xy plot that we already plotted from here, and this time choose the z coordinate 5. Okay, so it should be okay, this one. Now write to the file, and you can see that the values are negative and some are positive. So you have to like flip that thing. Okay, so write it down. This is X and this is the CP. So I will arrange data in the in this fashion, that from A to Z. Okay, and insert graph. Okay, so the values are starting from the 0 and it is on the negative side. So you can simply double click here, and you can like here value in the reverse order. Okay, so it should be on the actually on the x-axis, on the y-axis. Okay, so now in this way you will get the graph as required. Okay, and if I try to like you have to format the data so that we can even like make the lines as well. Right now it is like making the issue, only one line is like making issue here. Let's provide the okay, this is the issue actually. So how this can be solved? Okay, anyhow, you can directly display in the like these symbols, and that's okay. Okay. Okay, now let's check the like other variables. So like contour plots. So I display on the directly on 3D arrow file, and uncheck the global range and display the mesh. This looks like a very good graph actually when you display and present to the anybody. In the colors, make it default. I would suggest that for the interior with this graph, the black color will suit very well. Okay, symmetry should have the this is symmetry, so also we will make it as a black. Okay. here. Okay, so there's some discrepancy in the mesh, but that we can ignore right now, but you have to correct this one. Okay. Okay, so you can see this graph. If you make this picture looks very good actually when you display on your presentation. Okay, so you can take any view like this. Okay, so y plus is maximum y plus is 10, and please note that the file I'm going to provide you, that file will contain the data which is shown here. Okay, so that file also has a y plus, maximum y plus is 6, and y plus is making a lot of difference in the data, like a drag coefficient, other things. So definitely I would suggest that you should run the cases with the 2 or 3 meshes, and then you have to find out that the which one is going to give you the results which are mesh independent. Okay, this is very important step, and that we will cover also. So anyhow, right now for demonstration purpose, for the teaching purpose, this is okay, and definitely we will go through the mesh independent steps as well. So this is the wall y plus on the in terms of the contour plots. And now if I go for the xy plot, then definitely I will go for the turbulence, and from here I will go with the y plus, wall y plus, and the z coordinate 5, and click on the save plot. So you can see the maximum value is on the leading edge, and average value might be around like a 3 or 3.5 or 2.5 in between those values. Okay. So, okay, now the next thing is that I want to post-process these results in the CFD post as well. So, that you can do like many things we can do here. That I will go step by step. One of them is that you have to find out the drag and lift coefficients in the CFD post, and we will compare that what is the like a similarity in the Fluent and the CFD post. They are giving same or not. Okay, so results should be similar or same, exactly same. So now in order to open the file, what I'm going to do is that this is true for the both cases. Okay. So I will double click on the results, and this will open the CFD post. Okay. So here what I did is that, for example, if I tell you that how to do this thing, so let's do it on the fresh copy. Okay. So here I didn't do it. So for zero angle of attack, so I will tell you that how this can be done on this case here. Okay, this was already done. That's why you can see this graph here. Okay. Now I'm going for the few expressions here, and our final goal is to create the expression for the drag coefficient and the lift coefficient. But to define this lift and drag coefficient, what we need is that we need the new coordinate frame. For zero angle of attack, new coordinate frame is not required. Okay, because it's already on the zero angle of attack. But for other angle of attack, there are 2 ways to be doing that thing. One is giving the angle of attack, but that's that is done in the CFS, in the CFS pre, and then we can get the results directly there. But if you are doing it in the Fluent and then getting results to the CFD post, then the only way is that to get the data for some angle of attack, you have to define the new coordinate frame. So I will define it for zero angle of attack, and same is done. Only difference would be their angle of attack, that will vary in the both coordinate frame. Okay. So here I will go to the these are expressions for the lift coefficient, and the formula is that the lift coefficient is a lift force and divided by the 1/2 density at the infinite, means at the inlet, velocity square at the inlet, and the area of your 3D wing. 3D wing is I told you, this is having the like span wise is a 0.3 and its chord length is 1. So overall area that is facing the wind is going to be equal to the 1 into 0.3. So it's going to be the 0.3 meter square. So why we are doing this thing? Because when we divide by the area, this will be non-dimensional quantity and it's irrespective of the both dimensions, length and like a chord length and the span wise direction. So this is independent of these values. This is now, once we divide by the 0.3, now they are like a per unit area. Okay, they are now going to be per unit area. So this is valid for the any case. And if you have the sum, like you want to make the calculation for like a forces dimensionally, then you have to multiply with that area. For example, my new wing is 1.3 meters. Then I will multiply with the 1.3. I will multiply with the 0.5. I will multiply with like a same thing here. So if I want to get the drag force for some other like aerofoil length and the area, so I will multiply simply the CL and CD by the 1/2 density, velocity square and the area, and I will get the force for that particular dimension or the particular material properties and the flow properties. Okay. So now what we want that these should be defined like area, density and the velocity with the proper units. This is very important. If you define the some quantities directly, like I'm defining area directly here, so it's a 1 meter by 0.3 meter. So either you put the directly 0.3 and then you have to put in the brackets meter square, or I'm putting the 1 meter into 0.3 meter, then it will directly calculate the units and they are going to be meter square. Units should be like they should mesh very well. Otherwise we will get the values. They are okay, but the units will be wrong. And when I define the mass flow average of the velocity at inlet, because it already is containing the very like units, that's why we don't need to put the units in the expression here, because they are taking units from the CFD post itself, and the CFD post is taking data from the Fluent. And same is the case with the density. Okay. And then after that we define this function and these values here, and that's all. Okay. So now go to CFD post and go to expressions. So first thing is that I will define the density. So density, it should be a variable like an expression name that does not contradict with any other defined inbuilt name in the CFD post. Okay. So right click here and I'm going to use the CFD post, and mass flow average is very good for these definitions. Okay. And what we are doing with the density here. So find the variable that is the density, and where it's going to be on the inlet. Okay, location is the inlet, and if you apply you will get the units and the value as well, and it should be 1.225. Okay, so density is defined. Next is the like area aerofoil. So I will put the name in this way, so that the area might be a name of the some inbuilt functions, expressions in the CFD post. That's why I define the name. So that should be unique to like our own area, our own variables. Okay, so it's 1. So put the square bracket, and once you have the correct units, they will be converted. The units will be converted into the italic fonts. Okay, you can see it. Multiply with the asterisk symbol, then the 0.3, and then again put the units of the meter and click and apply. So this should give you the 0.3 and correct units, which is a meter square. Then I would get the velocity at the infinite. Okay, infinite means that the far away from our main geometry, that is on the inlet. So velocity infinite, and this is going to be the mass flow average. This is the velocity magnitude, so velocity only, and at the inlet. Okay, and it should be giving you 43.8. that is we defined the value at the inlet. Okay, now I'm going to define the, before that I will go to outline, and I will make the new coordinate system here. Okay, and that you can directly put from like here. Okay, this one. You can also do it from the insert, and from here you can also put the coordinate frame. Same icon, same thing. So one is from directly from the screen, one is from the menu. So you can put the name also, like you can say coordinate frame 0 angle, okay, 10 degrees, whatever you want to put. So let's say I'm saying it's the for angle of attack, okay. So now first thing is that simply click on the apply, okay. Reduce the symbol size to the 0.3 so that it should be like, it's okay for if you take a look from the like outside, like from here, this is now properly visible. But if you zoom to the arrow file, this is slightly bigger, okay, or too bigger. So symbol size, if you make it 0.3, this will be over here, okay. Now see, there are the three axes. One is the Z axis that is normal to the XY plane, where our angle of attack will be there, okay. And two of them are the X and Y axis. So first thing is that we have to fix our Z axis and our origin. So origin, if I like going for the moment coefficient, then I will be putting my reference frame at the 0.3 or 30% of the chord length, okay. In that case, my origin will be at the X is equal to, now this is X is along the flow direction, so definitely that will be along the chord length. So I will put the origin at the 0.3 on the X direction, but this will make my Z axis inclined. So the Z axis point should also move in the X axis, and then it will make it a straight line, okay. This is how the origin Z point works, okay. So they should be in the same line, okay. The XZ plane point is the first point and second point. They are defining the maybe that in some cases our arrow file is along the Z and Y axis, okay, ZY plane. So YZ plane, in that case we have to play around with the Z axis point. Z axis point in that case would be the next direction, like maybe the X axis is going to be our Z axis, okay. So then you have to put the particular point of Z axis at that location, okay. Right now Z axis point is on the 1, that means that the X, Y and Z coordinate 1. So this is in the Z axis, but Z axis may be like a third axis may be along the X axis. Then you have to put the 1 here, okay. Now here you have to put the only like coordinates of our angle of attack. So it's only X and Y. Right now this is on the XY plane, so X and Y. So for example, I'm just giving example. If my angle was 45 degrees, then I will put the cos of 45, and this is sine and cos 45 will be exactly same. So I will put both of them here. Okay, so they are at the 45. So x-axis is important here. Actually, this is at the 45 degrees, and the y-axis will be at 90 degrees. So now this will be at the 135 degrees. Now take example of for the, although it's not necessary because we have the y forces already in the CFD post. But if the y forces was not there, then to get the y lift force, we have to make a coordinate frame that will be where the x-axis will be along the y-axis. In that case, I will put the 1 and 0 for the x-axis. So this will rotate completely by 90 degrees. Okay. And for 10 degrees, definitely you have to put the value of 10 degrees. That is like a second case. And copy. And paste in the x-axis. This is like we define the angle of attack for the x is a cos component and y is the z component. So this is a sine 10 degrees, and you have to put over here and apply. So now this is a 10 degrees angle of attack. Okay, if we increase the size of the our symbol, so this is now 10 degrees angle of attack. Okay, and this is the procedure that to get the drag and lift coefficient in the CFD post. Secondly, the benefit is that once you have the you are done with the hard work, then the whatever values you put in the table and you run the new case with the new angle of attack, just change the coordinates here and the data will be directly given to you from in the table. So unlike the Fluent that you have to calculate data every time, once you calculate the drag and then you have to calculate the lift coefficient every time, put the angles and reverse and their sign, and there's a lot of hassle there. But in the CFD post, this is much easier. Once you do the hard work, then everything is very smooth and streamlined. So let's say definitely now for this case, the angle of attack is 0. So we have to put the 1 and 0 here. And for 10 angle of attack, we have to put the proper X and Y components. Okay. Okay, now go back to expressions. Now I will define the new expression. This is for the lift coefficient. Okay, so I will put the value that is just from CFD post, and this is a force X here. Okay, and where this is going to be on the aerofoil, and divided by what? Divided by the 0.5 multiply with 1/2 density velocity square into the area. So expression of the density, then the area square. So area square will be there. That is again like expression. So this is the area aerofoil. Not area, but the first we will go with the formula that is the 1/2 density into velocity square. So velocity infinite velocity. So velocity at the infinite, that is the here, and to put the square we have to put the this cap symbol and then 2 and multiply with the area. Okay, area of aerofoil, and then close the bracket. But this is going to be now, see, the value of the lift coefficient with the just force X will give you the force along the default coordinate system, which is that X is along the X-axis and Y is along the Y-axis, no angle of attack. So now you may ask the question where the coordinate frame will be put. So this will be put over here. So you have to on the X you have to put the 1 hyphen symbol. Okay, then go to the outline, and then you have to right click here and click on edit in like command editor. Why I'm doing this thing? Because I want to exactly copy the that spelling. Okay, sometimes you type the same thing, but because of the capital letters or small letters, this will make the problem. Okay, so that's why I'm doing it. I'm directly copying from, because this is already from the from the CFD post. Okay, so here you have to paste. Okay, and apply. So the value will be same definitely, because this is already defining the zero angle of attack. But with a 10 degree angle of attack, you have to put the, simply you have to go back, and you have to simply change the coordinate frame values here. Okay, now I was telling you that the benefit is that if you make a table here and simply go to expression and put the lift coefficient, you get the lift coefficient here. Okay, so it's you can write it down. It's a lift coefficient. Okay, now the second expression is for drag coefficient. So new, and this is the drag coefficient. Okay, sorry, this is the first one is actually this is the drag coefficient actually. Okay, so duplicate, this is the drag coefficient. Okay, this is a drag coefficient, and lift coefficient will contain the force in the y direction. So make it y, and click on apply. Okay, and here you can change the units and make the units as the simple fixed one, and maybe you can make the digits, number of digits to the 4. Okay, this is the lift coefficient, and the drag coefficient is going to be the drag coefficient. So expression and the drag coefficient. Okay, so this is the lift coefficient, and this is a drag coefficient, and you have to put the scientific to the fixed one, and number of digits are equal to 4. This is the drag coefficient. Okay, I told you values are slightly varying than the values I have in the slide, which is like on the main slide, which was the most important slide in the this workshop. So that contains a slightly variation there. Okay, in the drag maybe it's maybe lot of differences there, like it's a 0.225 and here is a 0.0173. Lift coefficient is 0.0123 and it's a 0.0125, so it's like lot of small difference here. It's a Okay, lift coefficient. Okay, so the lift coefficient, let's make the again the function here. Okay, so the force y. Okay, now this is corrected. Okay, so sometimes you have to take the directly the spelling and everything directly from CFD post. So now you can see that our values of the drag coefficient is 0.0123. Here's a 0.0173, and so this will this is more accurate here. This is more accurate here. Okay. But the lift coefficient is coming out to be the 0.2225. That's the problem actually. So let's work on that thing. Okay. Okay. So I verified the results, and it turns out that we were comparing the 10 degrees angle of attack case, and our case was the 0 degree. Right now I was explaining. So here. Okay. So I ran the case actually for the some iterations also, that so that I can confirm that it is not because of the solution, but it is actually a case of the 0 degrees angle of attack. Okay. So the lift coefficient is 0.2225, and this is the same, almost like a closed to this value. Okay. So double two triple 25, and in the previous case was the 0.225, and the drag coefficient is 0.0123. This is like a higher on the higher side, and from SST it was 0.00942. Might be that the SST was predicting the lamino turbulent transition slightly, but it was predicting, and that's why it was only a 17.75% error, and at higher angle of attack error is more. So now I think you get the idea that how to get the values of the lift and drag coefficient in the CFD post through the expressions. Okay. Okay, now you can display the vector plots as well. So that we display on symmetry 1 and apply. Okay, here you can go to symbol and make the symbol size initially the 0.1 or maybe less values. Okay. Okay, let's make it 0.04. Okay, let's make it 0.01. Even less value. Okay. Okay, here let's make it the 3D arrow like this one. Okay, here you can clearly see that the development of the boundary layer on the aerofoil upper surface. Okay, here I can change the aerofoil color as well. Let's make it gray and apply. Okay, so I think now we have completed the a lot of things in this case, and you can also display the path lines. You can display the contour plots, which we already did. So let's display on the aerofoil surface. Okay, here you can display the mesh lines and make the color as the black. and don't display the any faces. Okay, click and apply. Okay, so this will be like a nice picture for your paper or for your PowerPoint presentation. Okay, and secondly, when you're displaying the contour plots, here you can like change the number of levels to the like 20 and apply. Labels, you can put the numbers also on these levels, and there are show color bands. Okay, like this, and you can also turn off the color lines. And secondly, you can make the color lines color to be a single color, for example the black color. Okay, like this. Okay, so I think now the workshop is complete, and let's see the other things if required. So if you have any problem, please let me know. If you have any questions or queries, please let me know. Thank you. Okay, in this video I've explained that how you can get the drag and lift coefficients in CFD Post. So first thing is that if the angle of attack is 0, then there's no need to define the new coordinate frame. If the angle of attack is some values, then you have to define the new coordinate frame. Okay, so how this can be done? So now it's the exactly same procedure, and why it is so, let me explain why we are getting this thing here. Okay, so actually when you want to find out the lift and drag coefficient, so what is the basics here? Okay, the formula is that the drag coefficient is drag force divided by the 1/2 density at the infinite, means at the far away from the main body, that is the inlet, usually speaking. Velocity at the infinite, that is again the inlet far away from our main geometry, that is aerofoil or aircraft. This can be any geometry. And the area. Okay. And similarly for lift coefficient, this will be lift force divided by same thing here. Now the lift force and the drag force, they have the 90 degrees from each other. Okay, and the drag force or the drag coefficient is the like is the force that is in the same direction as in the relative wind direction here. Okay, for example, our aerofoil in the CFD, what we do is that we put the like a same angle, but in the actual case the aircraft will be having the different angles, and wind will have the same angle and the aircraft will be having the different angles, and so the aircraft wings. But in the CFD, what we do is that we do it slightly different. So we provide the like first 0 angle of attack case, and this is the chord length here. Okay, so this is the chord length here from here to here. 1 minute. Okay, so the chord length and the chord line is here. Okay, this is the chord. This is the chord line is a line, and the length is the length from leading edge to the trailing edge. This is the leading edge, and this is the trailing edge. Okay, so in this case, the drag will be along the same direction as the direction of the wind, incoming wind, and the lift will be normal to this one, the drag coefficient or the drag values. Okay, now if I have some angle of attack, in that case what will happen is that in this case, let's say now my relative wind angle, so it's the same thing like if the aircraft is making the angle and the wind is coming from bottom, so this is same thing alpha is here. Okay, so angle is important, the relative position is important, but not their actual position from the forces calculation point of view. Now what will happen is that in this case the drag will be on this side. Okay, and the lift will be tilted by the same angle, 90 degrees, but this now lift will be here. Okay, so now what we are doing is that in the CFD post, that if the angle of attack is 10 degrees, which is here, and the same angle which is the drag is making with the x-axis, so what we are doing is that we are just rotating our coordinate frame by 10 degrees, so that when we evaluate on these axes, new axis, because we are not putting any angle of attack in CFD post, not possible. Okay, so when we are in the new coordinate system, so when we put the force x on the like On the new x-axis, this is like you can say this is the x and this is the x new, and this is the y-axis and this is the y new. So now when you put the force x, now force x was originally for the x-axis, but now with the rotation of the axis, the force x will give you the values on the new x-axis. And similarly, the force y, that is a normal force, will give you the lift force on the new axis, on the new y-axis. Okay. So it means that now if you use the same formula, but with the new coordinate frame, what you are going to be getting, you are going to get the drag coefficient, the drag force at the new axis, new x-axis, and lift force at the new y-axis. Okay, this is the idea. Okay. So now here, what we are going to be doing is that we are going to be defining a new coordinate system. So first thing is that I will insert, and that can also be done from the quick access icons. And you can say this is for the angle of attack. Okay, here you have to put the origin, which is 0 0 0, and z axis point is 0 0, because x and y are 0 0. And some cases when the moment coefficient is to be determined, then this might be at the 30% of chord length in the x direction, definitely, because the length of the chord is, or the aerofoil length is along the x-axis. In that case, you might have to put the point at the point 3 and origin also at the point 3. Okay, right now just keep the values and click and apply. So this is for angle of attack 0 case. This is for the case for the 0 angle of attack. You can change the size of the axis by changing symbol size to the, let's say, 30%, 0.3, or even less value. Okay, so this is a new coordinate frame. This is the we defined, and right now it's exactly same as the global coordinate system. Okay, now if I want to give the angle of attack, so I will simply put the x and y coordinates that we have already calculated in our PowerPoint slides. So for 10 degrees angle of attack, the x component is this value. So put this value over here. Okay. And in the y-axis, I will be putting the sine 10 degrees, and this value is here. So this will be now rotated, this only xy axis, okay, not the z-axis. Z-axis is exactly on the origin, is put on the 0 0, and the second point is put at the z point as a 1. Okay, so 1 10 doesn't matter actually. You can put the 10, it will not make any difference. Okay, so vector is important, not the magnitude. Here the direction is important, not the magnitude of the vector. Okay, so now it is rotated by the 10 degrees. You can see here. Okay, this is making 10 degrees angle with respect to the x-axis. Okay, this one, this is the 10 degrees. It means that now what we are doing is that we are putting the that LED was there on this direction, and this is the chord line. So we are putting the relative angle of alpha is equal to 10 degrees. Okay, so lift will be along the green here, lift force, that is your y force, force y in CFD post, and this is the force x, but this is now on the new coordinate frame. Okay, so now this is done. We have defined the coordinate frame. Now we have to go for the expression. So the formula is this one. Okay, the formula is this one. So what we have to be doing is that we have to be defining these values. So lift force will be directly given by from the CFD post, and lift force also, that is a y force and x force. Lift is y force, drag is a x force. We will define these things in the expression. Okay, the formula is very simple. So first thing is that I put the density function, and the names should not be common names in the database of the CFD post, otherwise you will get the conflict. So put any names which define your name with a proper understanding, but should be not contradicting with the existing name in the CFD post. So I will use a function CFD post and mass flow average of what? Of the density. Okay, so the density, and we are at the inlet, that is far away from the our geometry of the aerofoil, okay, or the 3D aerofoil. So this is on the inlet, and apply. You will get the 1.225 with the units as well. Okay, then right click again and put the new expression. This is for the velocity at the infinite. Okay, velocity at the infinite, and right click here and go for the functions, and again the same mass flow average. And what you are going to be doing is that the variable is the velocity magnitude, so simple velocity, and location is at the inlet. Okay, so we get the same velocity, that is the 43.822, right? Okay, now the third thing is the area. So area I exactly know. So area of the aerofoil, that is the its length, chord length into the third dimension, that is the its span wise, that is the 0.3. So it is going to be the 1, and you have to put the units. Otherwise, when you calculate the variables, they will be having the problem in the units. So units should be done properly. For the variables defined already, they have the units itself from the CFD post, but for constant values, we have to provide the units by ourselves. So 0.3 and the meters. Okay, apply. You should be getting the 0.3 meter square, means 0.3 value, and meter square should be unit. This is done. So we have defined the three values in the denominator, that is the density, velocity, and the area. Okay, now define the expression, let's say we are defining the denominator. Okay, denominator. Okay, so I will put the everything together. 0.5 into this is going to be the the density. Where's density? Density should be here. Then the velocity, infinite velocity square. So expression for the infinite velocity, so you have to put the power symbol and 2 and multiply with the area. So right click here, expression, and the area of the aerofoil. Okay, and where it is here, it is should be area aerofoil. Okay, so click and apply. So you get, this is actually a dynamic pressure. So the units are in Newton. That is correctly done. Okay, now define the drag coefficient. So the drag coefficient, and here I will put the function CFD post, and it is the already they defined the force x in the along the x direction, because we are now going to refer to the our coordinate frame. So that will be different thing now. Okay, so where it is going to be, it is going to be at the location, that is the aerofoil itself, and then divided by the denominator. Okay, so again expression, this is going to be the denominator, and done. Okay, but this will give you the wrong results because we didn't put the coordinate frame here. So I will go to outline and right click here and edit in command editor and copy the name of the coordinate frame exactly from here. Okay, don't try to type it yourself because this is sensitive to the capital letters and small letters. Sometimes space is also important, so maybe it will not take the things correctly from directly inputting by the typing from keyboard. So copy it and go back to expression and double click here and put the one hyphen symbol here, underscore, and then control V. So this is the correct way. Okay, now click and apply. So we are getting the value of the drag coefficient to be the 0.00. See, the data I took previously from the SST model with some slightly different mesh with the Y plus, was slightly varying. Mesh size was almost same, but the Y plus was different. In that case, my 10 degrees angle of vertex CD was 0.0173, but here it's the 0.0172. Okay, so it's a slight difference is here, but if you round off the value, this will be 0.0173 exactly. Okay, now I will duplicate drag coefficient and I will put the lift coefficient here, name of the new expression. This is now duplicate name, so this will now take the new name, but it will have the same formula. Okay, so only difference would be that you have to put the force Y here. Okay, sometimes typing, I told you typing directly from here make the issues, but we can try. It is taking it very, very nicely. So previously the values were lift coefficient was 1.2727 2573, but right now it is 1.27035. Okay. But again, I would recommend that you can go to function and CFD post and put the force Y. Okay. And delete everything from there and just keep the coordinate frame. Okay. And like this, and click and apply. This is exactly same. Okay. Now you can save this thing into the table. So the benefit would be that if you do it in the table, so what will happen is that insert a new table. Okay. So benefit is that this will be will be saved into the CFD post, and whenever you run the new case and copy the complete cell and you put the new angle of attack here, I run the case and you will be getting the the values again by changing some values, the values will be updated automatically. In the Fluent, what we do is that we have to every time we have to put the angle of attack and get the left and drag coefficients. Okay, so here simply you have to right click here and expression, and you have to put the drag coefficient. Okay, enter, and second is the lift coefficient. So the lift coefficient and enter. Okay, so I will be changing their way of displaying the numbers. So I will go with a fixed one, and I will put the 4 digits here. Okay. Okay, so this is a drag coefficient, and you can also to make it readable, you can put the names here in the a text here in the same table. This is the lift coefficient. Okay. So now whenever you change anything in the a meshing in the your angle of attack, your turbulence model, this will be updated automatically. So how this can be done? For example, okay, first let me save the file, this one. Okay. Okay, now for 0 angle of attack, okay, let's move it here. Okay, so now for 0 angle of attack, this is here. So now what I can do here is that to get the values, because the best way would be that I should right click here and copy here, but now doesn't matter actually. So what I can do is that I can directly copy everything from the expressions here. Okay. Okay, so what I'm doing here is that I am creating the these variables there. Okay, same expressions. So I'm simply copying everything from there. Okay, so edit and copy, and let's see that can we do it or not. Yes, we are able to do it. Okay, then the area arrow file, the names can be slightly different, but the expression should be exactly same. Okay, and density now, the velocity at the infinite. Okay, so the velocity at the infinite, Control C and then Control V. Okay, then the drag coefficient. Okay, the drag coefficient is here. Now the thing is that the name of your coordinate frame should be correctly defined. Okay, if not, then you have to copy that one. That's not a difficult thing. Okay, so we have to define the denominator as well. So denominator. Okay, so area arrow file, this should be the name of the your expression. So copy and okay, duplicate. Okay, so we have the like a denominator. Okay, and its values are these ones. Okay. Now the next thing is that the drag coefficient. So let's see that do we have any problem? So no, we don't have any problem at all. And this is the zero angle of attack, and this is with the SST model. Okay, and that is very close to the data from the Abbott and yes, Abbott's theory of wing section book, that is giving the value of zero angle of attack 0.008. This is 0.0094. Okay. Okay, the next thing is the lift coefficient, and for lift coefficient we will copy the expression from here, the lift coefficient. Okay, so same name is for the coordinate frame number, this new one, that is the angle of attack. And this is the zero angle of attack actually. Okay, so now we can save the project file. Okay, so now this is the complete demo of the making the CFD post processing in the CFD post. Okay, and I have already given these slides with these commands. Okay. So I hope that you will like it, okay, and this will be helpful to you as well.